So this is a joint paper with Antonio Miralles and Jun Zhang. Here they are, Antonio and Jun. Antonio is at the Universidad de Messina, and Jun is at Nanjing Audit University. So it's so I think I will don't need a lot of time to present this paper. Maybe I'm wrong, so but I mean basically 1 hour is enough to present this paper at I think the level that makes sense for this type of online presentation. There are lots of more technical aspects of the papers that I'm not going to go into in the talk, but if you're curious, they're in the papers. Please take a look. So it's a paper on allocation problems. So allocation problems can be described by their primitives. There are agents who have preferences. There are objects, which you can think of as goods or resources, or maybe even bads, objects that people don't want. And you want to know who is allocated what. So for example, when you allocate jobs to workers, courses to students, chores to family members, I thought of this one in particular with everyone at home in COVID. The distribution of chores becomes a common issue, practical issue that we deal with. Organs to patients, schools to children, and offices to professors are examples. In allocation problems, we usually try to achieve some normative objectives, and the most common ones are efficiency, fairness, and when it makes sense, property rights. So we'll talk about these normative objectives in the talk. Efficiency is something you all know. It's a Pareto optimality. An assignment is efficient if there's no alternative assignment that makes everyone better off and at least one agent strictly better off. Fairness is something that sometimes economists don't think too much about, but it is very important in practical assignment problems. Policymakers care a lot about fairness. And today, fairness will be situations in which there's no envy. So 2 agents, Alice and Bob. Alice envies Bob at an assignment if she would like to have what Bob got. So an assignment is fair if there's no envy. No agent envies another agent. In my model, I will sometimes talk about discrete object allocations. I will be talking about allocating objects which are indivisible. And when I do that, I will always assume that I have access to randomization. And the reason is that when objects are indivisible, fairness requires randomization. If Alice and Bob want the same object, I have to flip a coin. So throughout the talk, I will, even when I'm talking about situations where the objects in question are indivisible, I will assume that I make them divisible by randomization. Pseudo-markets are artificial markets. So in a pseudo-market, we provide agents with a fixed budget of monopoly money. This is fake money or funny money. And we allow them to buy objects at market prices. So it's like a real world marketplace, but we set it up artificially to solve an allocation problems. And when the objects are indivisible, then we're going to allow them to buy shares or probability shares or fractions of the object. So here's a model, and this is not my model. It's an old model due to Hillel and Steckhauser in a famous paper in 1979. So they tell a story about assigning workers to jobs. In their model, an economy is a tuple where I is a finite set of agents, L is the number of objects, and let's assume that there is the same number of objects as agents. Each agent I has a utility function that is defined over all the bundles in RL plus, which add up to less than 1. So you should interpret this as being lotteries. So if I have a vector x in RL, it means that the probability that I get object L is XL. And they add up to less than 1 or equal to 1, which means that with probability 1 minus the sum, there's an outside option which I will get. So if I'm agent I and I hold a vector x, that describes a lottery over the object in L and the outside option. So that's why they have to add up to less than 1. So the agent's preferences is described by this utility function, which is defined over all these lotteries. An assignment is a vector of lotteries, one for each agent. So it's an xi for all the i's in I, with each xi being a lottery. And moreover, the assignment requires that if I add up what each agent gets for each object L, it cannot exceed 1. So if I add up all the vectors xi's, it cannot exceed the vector 1. So you can think of this as being the total supply of each object is 1. There's 1 copy available of each object, and I'm going to allocate it by giving each agent a probability share. And so when I add up over all the agents for each object, I cannot give them more than 1. And then there's a very famous way of creating one grand randomization, which will ensure that each agent gets this object with the corresponding probability. So I can allocate all the objects at the same time with this grand randomization, and that will be, so that's the Birkhoff-von-Neumann theorem. Yeah. Are there any questions about the model?
What's the interpretation of an agent receiving less than 1 total probability of getting something?
The interpretation is that there's an outside option, and they will so they will get the outside option with probability 1 minus the sum of the x's.
Okay. I would have expected the number of objects to be less than or equal to the number of agents rather than equal, but we'll see what happens.
Yes. I'm going to assume that utility is monotone increasing, so people don't like the outside option.
Okay, yeah.
They want one of these. So in this model, you will have that all the objects will get fully allocated.
Okay.
So Hill and Steckhauser look at market equilibrium. So I'm going to call that that type of equilibrium, I'm going to call it an HZ equilibrium. So an HZ equilibrium is a pair, an X and a P, where X is an allocation, so it gives each agent a lottery, and the sum of the vectors Xi's has to be equal to the total amount of object available, so it has to be equal to 1. And the P is a price vector with a property that each Xi solves the optimization problem for each agent. So this optimization problem is familiar, but slightly different from what you might be used to. It has each agent choosing an optimal lottery Zi, subject to the budget constraint that at the prices P, the lottery that they buy cannot exceed 1. So if you interpret this, condition number 1, the statement that all the excess has to equal to 1, that's a market clearing condition. Supply has to equal demand. And property number 2 says that Xi is indeed the agent's demand. So it's what they want to buy at prices P when their income is equal to 1. So this is why it's a pseudo market, because you don't account for where the income comes from. When we study market equilibrium in exchange economies, for example, we need to explain where agents get their income from. So we say that they get their income from they're endowed with some goods, and then they sell those goods in the market, and with that income, they buy other goods, and then that's how we explain where the income comes from. But in this model, we don't explain where income comes from. So people, when they enter a room, they're given a bundle of money when they enter the room, and they can use the money to acquire objects in this code. So in that sense, it's an artificial market. It's not it makes things easy because incomes are independent of prices. So we're used to thinking that all the complications in general equilibrium theory come from income effects, but here there won't be any really income effects. There won't be any general equilibrium income effects because income is independent of prices. And it's not a closed model because we don't explain where incomes come from. So I don't know if you're familiar with this old terminology of open models, closed models. That's basically what it means. Okay. So there's a theorem. So this is not our theorem. This is in Hill and Steckhauser. If you assume that each utility function is linear, actually you can prove this theorem with weaker assumptions. But if you assume it's linear, so you can interpret these as expected utility preferences because the X's are lotteries. Then Hill and Steckhauser prove that there is an efficient Hill and Steckhauser equilibrium, and moreover, all the Hill and Steckhauser equilibria are fair. So the assignment in a Hill and Steckhauser equilibrium is fair. The fairness part of this is immediate. Each one of these agents has an income of 1, and each one faces the same prices. So there can't be any income, no? Because if I were to envy what Alex got, I could just have bought what Alex got. So there can't possibly be any income, sorry, any envy. Efficiency is more delicate. In this model, actually, the first welfare theorem doesn't hold. And so there can be inefficient equilibria. There can be Pareto ranked HZ equilibria. But they prove that there exists one which is efficient. And in fact, the technique that they use for proving that there is one which is efficient is something that we are going to use as well. So I'll talk a little bit about more later. Now, I mentioned the general equilibrium model where income is generated by selling endowments. So here in Steckhauser have an example in their paper showing that if that is a source of income, then there may not exist equilibrium. So I will come back to this issue later in the talk.
Just a quick clarification, does HZ mean anything, or does it mean this is the efficient equilibrium for the model that you just described?
HZ just refers to Hill and Steckhauser.
Yes, so it's just the efficient equilibrium for this model. It doesn't have any other.
Yeah, I just call it HZ because I want to remind everyone that this is a pseudo market.
Understood.
Yeah, so that the income comes from selling your endowment. That's the idea. So what do we do in our paper? So we depart from the Hill and Steckhauser model by looking at allocations where there are constraints. So we're going to look for very general constrained allocation problems. And we're also going to also going to introduce endowments. So I will talk about endowments a bit later in the paper, but that's the idea. And I will go through a bunch of examples of what I mean by constraints. Try to convince you that the problem with constraints is interesting. So the key idea will be to price the constraints. So in Hill and Steckhauser, the prices of each good, you can think of those as the price of the supply constraint for that good. So if you think about the price of apples, you can think of the price of apples as the price of the constraint that says that the demand for apples cannot exceed supply. Why does that make sense? Well, because that constraints generate an externality. So if I buy apples, there will be fewer apples left for Alex. So by buying apples, I am, in a sense, imposing an externality on Alex. It's not the kind of externality that we normally worry about, because it's a so-called pecuniary externality. I can price it, and then that price will align my interests with efficiency, and so that there won't be any. So the effect that I cause through the scarceness of apples on Alex is captured by the price of Alex. So that's really the idea in our paper. The idea in our paper is that we price the constraint, and then the prices internalize the externalities that are generated through the constraint. And in equilibrium, the prices will be right, so that you will get an efficient outcome. The prices will do the job of internalizing this externality. So I'll talk through examples of what constrained allocation problems are, and why our approach can address these situations with constraints. So there has been a lot of activity in the market design community, in matching theory, around allocations with constraints. So one of the places where they started is in this very famous application in matching theory of matching doctors to hospitals. And there's a long-standing concern in practical assignment of doctors to hospital, that there are some hospitals which are not popular, people don't want to go there, and then you want to achieve a certain minimum amount of doctors in those hospitals, and then the allocation problem has to deal with that issue. So in our framework, we can deal with that. So we have an assignment problem where the agents of the doctors, the objects are the positions in the hospitals. The constraints are each doctor can get at most one position. That's a sort of unit demand type of constraint. And then there are constraints. There's an upper bound on the available positions. That's a supply type of constraints. But there's also a lower bound type of constraint, which is that you want to ensure that it's at least a certain number of doctors in each hospital. So the challenge is how you do that. And the way we're going to do it is that we're going to price the upper bounds in a way. We may have to introduce additional upper bounds, but we'll price them in such a way that there will be demand overflow to the least desirable hospitals. Here's another application to course bidding. So this is another, maybe a little less well-known, but also a popular application of market design. So here the agents are MBA students, the objects are the courses. There are upper bounds on course enrollment, so you can't have more than a certain number of students taking each class. So each class has a certain capacity. So this is a supply constraint. And then you can have lower bounds on mandatory courses. So everyone has to take, for example, these students don't know the statistics, so they all have to take statistics. Or it could be that if they take, one type of micro, then they shouldn't take the other type of micro. They can only take one of the two types of micros. So you can easily write down constraints that the student's assignment has to satisfy. And these constraints, it turns out, we need to massage them in the right way, but you can also price them, and you can get a market equilibrium which is efficient, constraint efficient. I'll explain what I mean by that, and which is achieved in market equilibrium. The third example is maybe unexpected. So the third example is a roommate problem. So here, I'm sure you've heard about this problem. It's a standard problem in matching theory. Everything is good in matching theory where there are true populations we're matching. We're matching workers and firms. Then we can achieve desirable outcomes. But when we're forming pairs from the same population, then we know that the problem is much more complicated. So here we're forming roommates, the agents of students, and we're forming pairs of students. So we can capture that in our framework by introducing objects which are also a copy of the set of students. Now, when an agent is assigned an object, they are really forming roommates because it's a copy. So if you have Alice and Bob, there's an Alice which is an agent, and then there's an Alice prime, which is just Alice's role as a roommate. Now, the constraints are that you can have at most one roommate. That's a unit demand type of constraint. But now there will also be a symmetry constraint. So when Alice is roommates with Bob, we must also impose that Bob is a roommate of Alice. So if Alice purchases a certain share in the object Bob, then the agent Bob has to purchase an equal amount of object Alice. So we can write down the problem, the roommate problem, as a constrained assignment problem using these symmetry constraints. Now, in the roommate problem, we know very well that there's no guarantee that you will have stable matchings. So we prove instead that you will have market equilibrium, in fact, efficient market equilibrium. And equilibrium is a form of stability. It's a form of ensuring that each agent is individually optimizing at the situation that you arrive at. So you may not have the game theoretic notion of stable matchings, but you will have this market notion of stability. Next, I want to mention the endowment problem. So here I'm choosing, there are actually many practical problems where endowments matter, but I want to mention one which is familiar to many academics, which is the assignment of faculties to office. So the agents are the faculty members in the department, the objects are offices. The constraints are that each faculty member should get exactly one office, and the offices are in limited supply. But now there is in addition the problem that the offices are currently assigned. So if you're going to reassign the offices, you need to ensure that the agents buy into this problem, that they accept the political reassignment of offices to agents. So each agent has to be at least as well off as they are in the current office that they have. So these are participation constraints or individual rationality constraints. And I'm going to show that we can also address these type of constraints with our framework. Let me skip, very popular application of matching theory, which has all of these constraints, is Kuntz. But let me skip this application. So before I tell you what we do, let me just mention what we don't do. And the reason is because, what we do will look sometimes like this, but there are also very significant differences. Now, our constraints, after you have massaged them, you can set up a very standard constraint optimization problems. You can pick your objective, social welfare function, could be, for example, utilitarian one. And you can think about looking at the constraint optimization defined by the constraints and by this objective, and decentralize the outcome using the dual variables as shadow prices. So this is a simple thing. You can, this is the type of thing we do when we teach students general equilibrium theory. And what we achieve is a version of the second welfare theorem where you decentralize some optimal outcome using prices. The problem is that if you remember the second welfare theorem, you need to compensate the agents so that they can purchase what they need to purchase in the outcome. But that means that the transfers, these income adjustments that you need to carry out, are endogenous. They are a consequence of the allocation you want to decentralize. That means that you won't be able to control agents individual incomes. And that means that you won't be able to achieve individual rationality or fairness. So this is a way of achieving efficiency, but it won't be a way of achieving fairness or individual rationality. So our prices are not going to be the dual price that you get from solving these objectives, although they will look exactly like that once I write them down, because when you price the constraints, they will look like the Lagrange multipliers, but they are equilibrium objects. They are not the dual variables. They will arise from a fixed point argument. Let me very, very quickly mention the related literature, and then at the very end, I can tell you more once you have seen our results. The idea of achieving fairness in markets is old, goes back to Berrian and Duncan Foldy. It's certainly here in Steckhauser. Constraints in allocation problems have been considered by many people in the market design literature in recent years. Here I have written down some of the first papers that do this. So Ehlers et al. Look at school choice and related constraint problems. And Kamada and Kojima look at the hospital application that I talked about before. There are two very recent papers that also look at markets as a way of achieving solutions with constraints. So the Kojima, Sun and Yu, and Gull, Pessendorf, and Sang papers do this, but they do this in, so Kojima, Sun, and Yu focus on allocations when there are transfers, and they look at when the constraints give rise to the property of gross substitutes. Gull, Pessendorf, and Sang look at situations where you can achieve the outcome, you can approximate the outcomes by a model with transfers. So the approach that these papers take are quite different from ours. Finally, the problem of dealing with endowment has been studied by long time ago by Andreu Mascolel, more recently by papers by He and by McLennan. And the way in which we solve the problem is clearly connected to how they do it. So let me show you a bit later how specifically we deal with endowments, and I can talk a bit more about the difference. And by the way, the paper has a very extensive discussion of the related literature. So if I don't get to it, please see the discussion there. All right, so here's the model. Let me give you some preliminary definitions first. So a pair A and B, where A is a vector in Rn and B is a scalar, defines a linear inequality. So the dot product here is the inner product between A and X. And the convention is that I put A and X on the left-hand side. A linear inequality AB has non-negative coefficients if A is non-negative. Any linear inequality A and B defines a closed half space. So the half space will be all the vectors X which satisfy the linear inequality. A polyhedron in Rn is the intersection of a finite collection of closed half spaces. A polytope is a bounded polyhedron. So two special polytopes that you have already encountered today are the simplex and the subsimplex. So the simplex are all the vectors in Rn which have non-negative entries and add up to 1. And the subsimplex are all those that have non-negative entries and add up to less than 1. So these are polytopes. When I will use this notation and often omit the n superscript. So here in the plane is an example of a polytope. I can start from a finite collection of points and look at the convex hull of those points. Then I can write down a finite collection of linear inequalities, and I can obtain the convex hull of that finite collection of points as the set of solutions to this set of linear inequalities. And this is a polytope. more preliminary definitions. So I'm sorry, these are definitions that you are all familiar with. So I'll do it quickly. A function U is concave if it satisfies the usual definition of concavity. It's quasi-concave, the upper contour sets or convex sets. The next definition is maybe a bit less familiar. So it's semi-strictly quasi-concave if whenever X gives me high utility than Z, then for any strict convex combination, the strict convex combination is also above Z. So it's a strengthening of quasi-concavity, where I want to ensure that when I take a strict convex combination between X and Z, I don't hit the boundary of the upper contour set. And then when it's linear, I will often say it's expected utility. I will first discuss the model of an economy where there are no endowments. And I will present the main results for the case where there are no endowments. So this will look a lot like the Hirsch-Steckhauser model. An economy is a tuple in which I is a finite set of agents, O is a finite set of objects, and I'm going to assume we have the same number of agents as objects. Zi is consumption space. Zi will be a subset of RL plus. Ui is I's utility function, and QL is a strictly positive number, is the amount available of good L. So it's the total aggregate supply of good L. An assignment is in an economy is an XIL for each I and for each L, such that the vector Xi is in I's consumption space. Script A denotes a set of all assignments in gamma, and I'm going to say that X is deterministic if each XIL is an integer. So deterministic assignments are often important in applications because constraints are imposed on the deterministic assignments. For example, unit demand constraints require that for each agent I, if I add up what they get over all the goods, it cannot exceed 1. So the total amount of objects that I gets is not more than 1. Supply constraints is for each L, when I add up over I don't exceed the total amount of good L that is available. So there are other constraints that are used in applications. For example, lower bounds. So we call those floor constraints. And you can use floor constraints or lower bounds to talk about the minimum number of doctors that have to be assigned to hospitals in a rural area, or a lower bound the number of minority students that are assigned to particular schools, or like in the course assignment problem, to ensure that all students take at least 2 math courses. Now, a deterministic assignment is feasible if it satisfies all the exogenous constraints. Now I can define feasible assignment as being all those that lie in the convex hull of feasible deterministic assignments. This convex hull is a polytope because the number of feasible assignment, deterministic assignment, is bounded and therefore finite. So in our model, we don't need to start from the deterministic assignment. We are instead going to take as primitive an explicit, a set of feasible assignments. And we're just going to assume that it is a polytope. So instead of starting from a story for where the constraints come from, we're going to be very general, and we're going to allow for the set of feasible assignment to be any polytope. So our primitive would be a set C of feasible assignment, and that would be how we describe the model. So a constrained allocation problem is a pair gamma and C, in which gamma is an economy, and C is a subset of the set of allocations, is a polytope. And we refer to C as a set of feasible assignments in gamma. Questions?
easy to define the polytope based on a practical problem as those that you mentioned before?
Okay, Gerardo, can you speak a bit louder?
So given one of the problems you mentioned before, or the hospitals, the roommates, and all those, would that be easy to define the polytope based on the context of the problem, of the real problem?
Yes. Defining the polytope is easy. What's not going to be easy is what I'm going to do next. I'm going to do a pre-processing of the constraints. And that's where the complication lies. That part is, in general, tricky. And a lot of what we do in the paper is we work that out. We do the pre-processing for different applications.
Thanks.
But that's the part that it's more technical and that I'm not going to go through in the talk. Any other questions? So, like I said at the beginning, there will be normative properties that we try to achieve. The first one is efficiency. We need to talk about constraint efficiency, but the definition is really the natural one. It's what you think it is. A feasible assignment is weakly C-constrained Pareto efficient if there's no other feasible assignment, which is strictly better for every agent. A feasible assignment is C-constrained Pareto efficient if there's no other feasible assignment, which is at least as good for all the agent and strictly better for at least one agent. So weakly constrained Pareto efficient and constrained Pareto efficient really is what you think it is. Fairness is also going to be what you think it is, but it's a little bit more complicated to explain. So there won't be any, so the fairness will involve ruling out envy. But it may be that the constraints treat Alex and me differently. So in a constrained allocation problem, it may be that the constraints single out one of us in specific ways that will necessarily create envy. So I'm going to say that an outcome is fair if there's no envy that can't be traced to the constraints. So for that, we will need to say that two agents are of the same type if the constraints treat them in the same way. And then what we'll be able to show is there won't be any envy among agents of the same type. And there are many applications where all agents are of the same type. For example, the hospital problem is an example where all agents are of the same type. Okay, the next step is what we call the pre-processing of constraints. And so here what we're going to do is we take the set of feasible allocation C, and we look at everything that is in C or below. That's called a lower contour set. So the lower contour set is a set of all the vectors X in RL plus, which lie below some X prime in C. Okay, I'll show you a picture in a moment. Now, the reason we work with a lower contour set is because we can describe it through linear inequalities which only involve non-negative coefficients. So this lemma here is something we borrow this idea from a paper by Ivan Balbusanov, who uses it to talk about the probabilistic serum mechanism. So we use it here to, instead of working with a full set of linear inequalities, with the original set of linear inequalities that defines E, we only work with linear inequalities which have non-negative coefficient. And the advantage of that is that we can price them. And then, those prices will be not negative, and then they will behave in the way we want them to behave. So the lemma says there's a finite set omega of linear inequalities with non-negative coefficients such that I can achieve the lower contour set at the intersection of the half spaces defined by those linear inequalities with non-negative coefficients. The idea in the lemma is simple, so I'll show you with a picture. So here's my original set of feasible assignments. It's a polytope. And I can define it through the linear inequalities A1, A2, A3, A4, and A5. Now, to talk about the lower contour set, I will get everything that is in C and below. So to get at the lower contour set, I can introduce two new inequalities, A7 and A6. And note that A7 and A6 point out in are true, meaning that these normal vectors that define the linear inequalities have non-negative coefficients. And then the lower contour set will be defined by these three linear inequalities with non-negative coefficients. So I have my old inequality A3 and these two new inequalities, A7 and A6. And like I said before, in the paper, for each of the applications that we discuss, we carry out this computation, this pre-processing of figuring out what these linear inequalities must be. And that's where a lot of the work in the paper lies. Okay, so now imagine that I have done that. So I started from my set of feasible assignment C. I worked out this collection of linear inequalities with non-negative coefficients, omega. Now, for each one of these guys, I'm going to now analyze each of them. And so for each one, which involves a vector of coefficient A and B, I can look at the support of C, meaning all the pairs of agent and object which has strictly positive weight, strictly positive coefficients in A. Then there will be two types of inequalities. There will be inequalities where B is 0. So for those, what this is really saying is that agent I cannot consume anything of object L. So we're going to say that agent L is a forbidden object for agent I. In fact, all those constraints, you can just collect them into one grand constraint, which will just say which objects are forbidden for each agent. And if no object is forbidden for any agent, then I'm just going to create an artificial constraint which has the 0, the null vector as the coefficients, and then B will be 0. So imagine that I collected those constraints into here, and now let me look at the remaining constraints. Now, among the remaining constraints, there are some which only involve agent I. So I will say that that is an individual constraint for agent I. How do I know that it only involves agent I? Well, because the coefficients are 0 for all the other agents, for all the other groups. So omega I will collect all the constraints which only involve individual I. Okay? Very good. Now let me look at the remaining constraints. These are the really tricky ones because these involve more than one agent. So I call these omega star. These constraints are going to be priced. So these are the constraints which are the type that I described before. If I buy apples, there will be less apples left for Alex. So in order to internalize the effect that my purchase of apples have on Alex, I have to pay the right price for apples. So these will reflect the scarcity of apples. Now, in our model, we will deal with all constraints in the same way, all the constraints in omega star, because these constraints create these pecuniary externalities that, when one agent bumps into that constraint, they are affecting to what extent the other agents are allowed to bump into that constraint. So we'll assign a price to each one of those. And then, in a sense, what the theorem will tell us is that there are equilibrium prices which aligns everyone's interests with regard to those constraints, so that these externalities do not create any inefficiency. Any questions about this?
Is there any way to describe the pre-processing of constraints along the lines of an auction?
Not that I know of. I have this, the geometric intuition is very simple. It's basically what I told you. And the proof of the lemma is simple. It's is just, once you look at the lower contour set, it's a standard idea that you can just support it. If you look at all the supporting hyperplanes, they will only involve non-negative coefficients. Once you throw in, it's a standard way of doing it. But that's the geometric idea. I don't know if there's any economic way of interpreting this. I have to say, in each application, this is the hurdle that you have to overcome. That you have to work through the set of constraints to figure out what this is, and that can be quite tricky. So, for example, for roommates, it relies on some old results in combinatorial optimization. So that's sort of where the art of applying this lies. Okay, so I have two types of constraints: the ones that tell me that one agent can't get some objects, and the ones that restrict an individual agent's consumption. And then the other constraints are the ones that involve more than one agent. So I take the first type of constraint and I use those to define the consumption space for each agent. So the consumption space will simply be all those vectors that satisfy the forbidden object constraint and the individual constraints for agent I. So I use those to define consumption space. Okay? I won't use prices to define consumption space. I don't need to price those constraints. Okay? For example, unit demand constraints are individual. They tell me that each individual agent cannot buy more than one unit. So that will go into the consumption space. Supply constraints involve more than one agent, and therefore I will, I will need to price those. So for each one of the non-individual constraints, so these constraints that involve more than one individual, we define a price PC. And when agent I buys good L, they will have to pay to the extent that they are involved in the constraint that is defined by A and B. So they will have to pay for constraint AB. They will have to pay AIL times P of the constraint, the price of the constraint. So if you think about what you would do if you were to solve this, constraint optimization problem, when you look at your Lagrangian, you will have shadow prices for each constraint. And then when you distribute the shadow prices through the linear constraint, you will get exactly this type of form. So this is what I meant when I said that it will look like as if you were getting the prices from the dual. Okay, now I'm in a position to tell you what fairness means. So we say that two agents, I and J, are of equal type if they have the same consumption space, and if for every one of the constraints which involve more than one agent, the coefficients are the same for I as for J. So, like I said before, in many cases, all agents are of equal type. For example, the rural hospitals problem or the Hirsch-Steckhauser problem, they all have all agents being of the same type. So an assignment is envy-free if there's no envy. It's equal type envy-free if there's never any envy among agents who are of equal type. Now I can talk about equilibrium, and this would be the adaptation of the Hirsch-Steckhauser notion of equilibrium to the problem of constraints. So a pair, X star, P star, is a pseudo-market equilibrium for this economy with constraints, C, if each agent is optimizing when they are buying X star I in their consumption space. And when they face a budget constraint that they have only $1 available. Moreover, the total assignment obtained is feasible, it's in C. And finally, this is sort of a complementary slackness type of property. Whenever the constraint doesn't bind, the price is 0. So this is what we call a pseudo-market equilibrium.
Federico?
And the main, yes.
Can I ask you something? So I guess, you know, my geometric intuition tells me that you're going to have an equilibrium at an extreme point of the polytope, right? Of the polytope C. And if so, you know, will an allocation be supported by multiple prices?
Yes, I mean, in a sense, you can, once you have an equilibrium, you can recreate the second welfare theorem type of thing, and then you can show that this will, you know, with suitably chosen utilitarian weights, you can get this as an optimum. So you're right that this is this will lie at the boundary of this polytope. I'm not, you know, I'm not sure they have to be at the vertex. So it could be that in a sense there will be a unique supporting price.
I see.
Okay. But yeah, we have no results about uniqueness. So I really cannot say anything about that. I suspect that uniqueness of allocations, equivalent allocations will be very hard to get here. Mm-hmm. But then for each allocation, uniqueness of prices, I have no idea of whether we could get something like that.
Thanks.
Any other questions? Okay, so the main result of the paper is that if each utility function is continuous, quasi-concave, and strictly increasing, then there will exist a pseudo-market equilibrium in which each x star is weakly C-constrained Pareto efficient. And if, moreover, we strengthen quasi-concavity to semi-strict quasi-concavity, then there exists a pseudo-market equilibrium in which the allocation is not only weakly C-constrained Pareto efficient, but actually fully C-constrained Pareto efficient. So for example, for the expected utility preferences that I mentioned before for Hill and Steckhauser, in the application to Hill and Steckhauser, you do get a fully C-constrained Pareto efficient equilibrium. And moreover, every pseudo-market equilibrium assignment is equal tribe MV-free. So this is a situation where you will get a similar phenomenon to what Hill and Steckhauser get. The first welfare theorem doesn't hold. You can get Pareto, you can write down examples of Pareto ranked pseudo-market equilibrium. However, using the same ideas as in Hill and Steckhauser, you can prove the existence of one which is also C-constrained Pareto efficient. And the idea there is that since agents may be satiated here because of the constraints on their consumption space, it may be that they're indifferent among multiple bundles that cost differently. So what you need to ensure, and this idea is not ours, it's in Hill and Steckhauser, you need to select from the demand correspondence, you need to select the cheapest bundles. In a sense, this is making sure that people use money the right way. So I'm equally happy buying X as buying X prime, but X costs more, then I'm nicer and more conducive to an efficient outcome if I always select the cheapest thing among all the things I like equally well. So that's what that's how we deal with the issue. Okay, now I want to talk about. Let me see how I'm doing with time. Oops, I'm really don't have a lot of time left. Wow, I thought I was going faster. So Alex, for how long do we go?
Up to 15, something like
15,
that.
okay.
Yeah.
Yeah, so let me do this a little bit faster. So now I want to augment the model to also allow for an endowment vector. Now each agent I is described through a utility function and an endowment vector omega. And I assume that this endowment vector decentralizes all the aggregate supply of each code. So when you add up how much each agent has of good L, it's what it gives me a total amount of good L available. Now the model is very familiar. I could define well-rational equilibrium, just like in the textbook model of an exchange economy. So well-rational equilibrium is a pair, an X and a P, where now the total sum of the excess has to equal aggregate supply. So this is market clearing. Aggregate demand has to equal aggregate supply. And each agent is optimizing within their budget sets. Now, what is funny about this model, I'm sorry, this should be in the consumption set, not only in the subsimplex. So if you only have unit demand constraint, this is what the consumption space looks like. But where this departs from the standard textbook model is that there may be constraint on consumption space. And so in this particular case, where there's a unit demand constraint, Hill and Steckhauser show that even with very well-behaved preferences, you may not get existence of well-rational equilibrium. So here's a picture showing you what goes on. So remember, in the textbook model, budget sets look like this. When prices are P, endowment is omega I, then the endowment has to lie on the budget line, because you can always buy back your endowment at the market prices. And when you do that, you will exhaust your income. But now, in addition, with a unit demand constraint, you can't buy anything outside of the simplex. So your effective budget set will be this shaded area here. It's everything that's below the budget line, but also below the simplex. If you think about this, this will be this type of, even though it's a nice looking, the budget set is compact and it's convex. It doesn't have any of the obvious problems you may think of. It will lead to issues when you try to prove existence. You have failure of Walras law, because I might want to choose something here, in which case I don't spend all my income. So Walras law would be violated. And you also get that if I may be buying something at the corner where my demand becomes non-responsive to price. So these are suggestions that the standard ways in which we get existence will run into problems. In fact, here's a specific example. This example is from Peter and Steckhauser. So here you have three agents and expected utility. The three agents have utility functions, U1, U2, and U3. And there are three objects. But I want to assume that two of the objects are identical. So there's object A and then two copies of object B. So now the utility functions are that agent 1 gets 10 utils if they consume 1 unit of object A, and 1 util if they consume 1 unit of object B. Agent 2 has identical preferences to agent 1, and agent 3 has in a sense the opposite preferences. They get 10 utils from object B and 1 util from object A. Their endowments are 1/3, 1/3, 1/3, but since I lump together the two copies of object B, it's 1/3, 2/3. By lumping it together, I can draw a picture. That's why I do it. Now, the obvious allocation, if you want, is to give agents 1 and 2 a 50-50 share of their favorite object, object A, and then a remaining 1/2 share of the least favorite object, object B. Agent 3, who really likes object B, can just get the whole copy of object B. So here's a picture, the simplex. The obvious allocation is to give agents 1 and 2 this point, and to give agent 3 this point. But now imagine achieving this in equilibrium. Well, the prices have to pass through the endowment. So which prices can I write down so that agent 3 wants to buy this thing here, so agent B has to be able to afford this and want to buy it, and agents 1 and 2 have to be able to afford and buy this object. Notice that all 3 agents have the same endowment and they face the same prices, so they will, face the same budget set. So you need to come up with the same budget line that will do the job for all the agents. If you think about it, the only way I can do that is if I write down prices for which are the same for both agents. The prices have to align directly with the budget line. But if I do that, then agents 1 and 2, I have to remember to point with a mouse instead of pointing with a finger is not a good idea. Then agents 1 and 2 will buy something in this corner, so there will be excess demand for object A. Does that make sense? So, moreover, like I said before, the first welfare theorem fails, and there are Pareto rank relation in equilibrium. Okay, so here's what we do. So this is the model with endowments. So an economy is now a tuple, like before, a finite set of agents. Then each agent is described through consumption space, through a utility function, but now also an endowment, omega I. Aggregate endowment is omega bar. And I can define, as before, a constrained allocation problem where gamma is an economy and C is a set which we take as a primitive, we assume is a polytope, and we call the elements of C, we call them the feasible assignments. Now, I need to assume that the original endowment is feasible. Okay? So in the model with endowment, we also have a primitive set of constraints that is a polytope, and we assume that the endowment is feasible. Now, a feasible assignment is acceptable to agent I if it is at least as good as given that agent their endowment to consume. X is individually rational if it is acceptable to all agents, and it's epsilon individually rational if it is individually rational by epsilon. Now, just like before, I start from my polytope of constrained assignments, of feasible assignments. I pre-process the constraints. I get my set of non-negative constraint with non-negative coefficients, and then I use all the ones that only involve an individual to refine consumption space. So I get this script xi as the consumption space, and I get omega star as a set of non-negative constraints. Now, two agents are of equal type if not only do they have to have the same consumption space, and they have to have the same role in all the constraints, but they must also have the same endowment. Now, the notion of equilibrium needs to be adapted, because I mentioned already before that if you allow the income to be the standard valuation income, then you will get non-existence of equilibrium. So instead, we have a parameter alpha here, and we're going to say that for alpha number between 0 and 1, X star P star is an alpha slack equilibrium if X star is optimal for agent I in their consumption space, subject to this now different budget constraint, where their income is a convex combination of the Hill and Steckhauser income of $1 and the valuation income that they get from selling their endowment at the equilibrium prices. So notice that if alpha is 1, then this is the same as in Hill and Steckhauser. And if alpha is 0, then this is the standard valuation income. So in general, the alpha gives me a convex combination between the Hill and Steckhauser income and the valuation income. The resulting allocation has to be feasible. And just like before, when a constraint is not satisfied with, is not binding, then the price must be 0. Now, the main result is that we get the analogous statements we had before, but for alpha constraint. So I need to assume that the aggregate endowment is strictly positive for each constraint, for all the agents and the goods that are involved in the constraint. So the idea here is, it's a familiar idea from when you need to go from quasi-equilibrium to equilibrium. You need to deal with agents having 0 income. So here, what allows us to deal with that is this strictly positive endowment property. So now what matters is that for each constraint, the endowment for that constraint to be strictly positive. But if you have that property, and if moreover each utility function is continuous, quasi-concave and strictly increasing, then as long as you're not in the valuation case, so as long as alpha is strictly positive, we get an alpha slack equilibrium where X star is weakly C constraint Pareto efficient. And moreover, if the agent utilities functions are semi-strictly quasi-concave, then there exists one equilibrium which is also C constraint Pareto efficient. And finally, any alpha slack equilibrium assignment is equal type MB free for the same reasons as before. This is just the same ideas. Okay. Any questions about this result? Okay. Now, I told you that we could also get individual rationality, and this is how that works. So, I mean, let me say just a word about what alpha does here. So in a sense, the way, so if you look at the, alpha here, so we need alpha to be strictly positive. So what alpha does here is that it gives prices nominal meaning. So in the valuation model, if you multiply the price factor by positive scalar, the budget constraints do not change. But here they do change. So because the alpha is not affected by the scalar multiplied by the prices. So this gives a little bit of sort of monetary illusion. It gives a nominal also prices. Now in this model, you need to allow some prices to be 0. So what this allows us to do is to give us an independent way of getting an upper bound on prices. We can find sort of choke prices. Because of alpha, we can find prices that are large enough that there can't possibly be any excess demand when those prices. So that's sort of the crucial idea for how alpha helps here, at least in how we solve this problem. But now you might think that alpha doesn't have any meaning when the prices are endogenous. Maybe if I change alpha, then prices will just change with that. And I, a small alpha or a big alpha it can possibly make a difference. So this theorem is meant to show you that that is not true. So this theorem says, for any epsilon, there is an alpha small enough such that if you look at the agent's optimization problem in the Waldration model, so when the income is the Waldration income, then the utility that they can achieve if they were to face the Waldration budget set is as close as possible, is within epsilon of what they achieve in equilibrium. Okay, so this is saying that I can, in a sense, approximate the utility that agents get in the Waldration model by choosing alpha to be small enough. I know that I can have Waldration equilibrium by taking alpha equal to 0, but by taking alpha small enough, I can ensure that agents' utilities, level of utilities are as close as I want to utility that they would get if they were facing Waldration incomes. So in particular, I can get them to be as close as I want to satisfying individual rationality. Okay, so this is what I meant in the beginning when I said we could deal with participation constraints. So for an epsilon, I can get you to be as close as possible to the satisfying individual rationality constraint. Okay, and I will use the last few minutes to explain a little bit better the connection to the literature. So this idea that when agents face the same prices, they have the same income, then there can't be any envy. That is sort of the fairness built into competitive markets. That idea is, of course, old in economics. The Arian paper I'm citing here is a paper by Duncan Foley from around the same time. It also makes that point. It is also the part of what's attractive about the Hill and Steckhausen model. There's a more recent work by Budish using that property in course allocations. Then the literature on allocations with constraints has different motivations. A lot of people think about constraints in the school choice literature, where you want, the constraints because they ensure some diversity or affirmative action type of objective. So the Ehlers, Haffali, Yilmaz, and Yildirim paper deals with that type of constraints. There are many papers which look at the hospital interns problem with constraints, and there's a particular application to the Japanese assignment of hospital interns. So there's two influential papers by Yuichiro Kamada and Fujito Kojima, which introduced that problem. The problem that I talked about getting existence of equilibrium when there are in the evaluation model with endowment, that was first studied by Mascolelli in a paper by 1992, where he makes an adjustment to income, which is similar to what we do, but in his model, the alpha constraint, the alpha property is endogenous. So that doesn't allow him to do what we do so that you can control the alpha so that you get individual rationality. The recent paper by Hayes is really very close to ours, in the sense that he's also trying to solve general. Of course, he doesn't have constraints. It's not. It's a problem that's only about the assignment issue, not about the constraint. But the issue of how to deal with endowment is also similar to how we do it in our paper. He can't get the type of fairness guarantee that we have because he can in particular get envy among equals. So that how we are doing it doesn't allow for doing that. And McLennan approach is also similar, using an alpha type of component to the income, but in his case, the role of the alpha is as a way of operationalizing transfers between agents who are satiated and agents who are non-satiated, so that the role of the transfers is quite different. The role of the alpha is quite different in his solution as in ours. And like I mentioned before, there are also 2 recent papers which also think about using markets to solve constrained allocation problems. But the techniques are quite different in their cases from others. So it's, and like I said before, there's a long discussion of related literature in the paper, so you're happy to look at that. You should look at that if you're curious about more connections. But yeah, I should stop here.
Right. Well, thank you so much. We're just about on time. Is there perhaps any last question?
Can I ask a question? Or
Should.
so suppose that some of your constraints are like soft constraints, in the sense that there is a target. If we move away from that target, there is a cost, but it can be violated. And for the sake of the argument, suppose that these costs are like nonlinear. So is your setup going to allow for such a thing?
No, it does not. Yes, it's important. So in our case, the constraints are either satisfied or they are not satisfied. And so you have to be able to write a feasible constraint as this polytope.
Thank you.
All right. Well, thank you everyone for joining. It's been great to have you, Federico, and hopefully see everyone next time. And thank you once again, Federico. Thank you.
Oh, thank you. Thank you.
Thanks, Federico.
Thank you.
Bye-bye.
I enjoy.